Good morning. Hopefully you guys had a good weekend. We're going to go into the second half of this unit, which is graphing rational functions. So what I would like you to do is first do this page on your own. It is all review from what we did third quarter and a little bit of first semester. So pause this here and see what you can do on your own first. All right, so hopefully you've tried a bunch of the problems. So the first thing, you're going to define a function. Remember, for every input, there is exactly one output. So if you think back to first semester, we talked about if we had a table of values that the x value could not repeat. We didn't care what the y did, but in order for it to be a function, the x value cannot repeat. And if you remember when we talked about a graph, we had what we called the vertical line test. If it only hit once, then it was a function. If you could drop a vertical line on a graph and it hit twice, then it was not a function. Okay, so just some things to think about from what we talked about first semester. Okay, and second semester, the biggest function we looked at was x squared. Remember, x squared is a parabola. It's going to be U-shaped. We spent almost all of third quarter looking at parabolas. And we also talked about how we can shift parabolas. And we kind of started that first semester. So if you remember, we kind of had a generic form of x minus h plus k. And remember that h was your horizontal movement, and that k was your vertical movement. We started it in first semester when we looked at absolute value, when we looked at linear functions. We looked at quite a lot of different pictures. So this plus 7 means we are going 7 to the left. Sorry, that's an L. And then we are going, I'll write that over, 7 left. And then the plus 5 means we are going up 5. For the second one, if we're subtracting, remember that means we're going to the right. And then the minus means we are going down 32. So we are going to deal with the shifting today as well. Then we also talked about vertical and horizontal lines. Hopefully you remembered that if it is a horizontal line, you're always going to have y equals a number. And if it's a vertical line, you're always going to have x equals a number. And that's going to become really important in the second half of this unit. So here I'm hitting the y-axis at 2. So this would be the equation y equals 2. Here I'm hitting the y-axis at -3. So this would be y equals -3. And then for the bottom two, here I'm hitting the x-axis at -2. So this would be x equals -2. And here I'm hitting the x-axis at 1, 2, 3, 4. So this would be x equals 4. So you need to remember that vertical is x equals a number. Horizontal is going to be y equals a number. Okay, so we're going to use that moving forward as we start talking about graphing. So in the first half of the unit, we looked at rational functions, but we were mainly adding, subtracting, multiplying, and dividing them. We also did a lot of factoring, which we'll also use for the graphing portion as well. The biggest thing is you have to remember is you can never ever divide by 0. So you can never have 0 in this denominator here. So one of the things we're going to be looking at is if there's a value that makes this go to 0. So if you can kind of think in your head, what would make this equation go to 0? And if you can't think of it, you can set up an equation. So if I say x plus 2 equals 0, that means x equals -2. That means if I were to solve or to graph this, when x equals -2, this would be undefined. And this is going to lead into what we're talking about today. It's going to be what we call an asymptote, which we'll get to in a second here. Anytime you have something that's undefined in the denominator, it is going to create what we call an asymptote. An asymptote is going to be an invisible barrier that your graph approaches but never crosses. And usually when we graph an asymptote, we're going to be using a dotted line. So dotted lines are going to represent your asymptotes. So let's actually take a look at what I mean here. So we're going to start by graphing this equation. This is going to be my parent function. Okay, and just like with quadratics, we'll eventually shift them. And if you're talking about shifting this graph, it'd be very similar to a quadratic. We'd have 1 over x minus h plus k. So that h is still going to be your horizontal movement, and that k is still going to be your vertical movement. So if you were to shift this parent graph, this is what it would look like. Just like for quadratics, we had y equals x squared as the parent graph. So that's how we got our shifted graph of x minus h squared plus k. So very similar. The difference here is that horizontal movement is going to be in the denominator. The vertical movement is going to be outside. So let's sketch the parent graph first. So when you start a graph, you're plugging in your values for x. So if I plug -4 in, we get 1 over -4. So that's going to be -1/4. Sorry, that's a 4, small space there. If I plug -3 in, I'm going to get -1/3. -2 is going to give me -1/2. -1 is going to be 1 over -1, which is going to simplify to -1. Here's that special case. If I put 0 in, I have 1 over 0. We can't have 0 in the denominator. So this is what we call undefined. And we'll talk about that in a second here when we graph it. So if we do the positive numbers, we're going to put a 1 in. 1 divided by 1 is 1. 1 over 2, 1 over 3, and then 1 over 4. So we're going to graph this. So if I graph the ordered pair, -4, -1/4, you're just going to have to eyeball it. We've got -3, -1/3, -2, -1/2, -1, -1. And I know it doesn't look like it, but this is actually going to form a curve that's going to approach both the x and the y-axis, but it's never going to cross it. So if we do the same thing for our positive x values here, we're going to have 1, 1, 2, 1/2, 3, 1/3, 4, 1/4. It's going to look very similar. In fact, it should be a mirror image, but on the other quadrant. Again, it's going to get closer and closer to both the x and the y-axis, but it's never going to cross it. Both of these axes are going to be what we call asymptotes, because it's approaching both of these values, but it's never going to cross it. So this is where those kind of dotted lines come in. So I'm getting closer and closer to both of them, but I'm never going to cross it. And that is what we call an asymptote. And our asymptotes are actually going to be equations. So remember, vertical, that's up and down, and we've got horizontal. So if you remember, vertical means we're always going to have x equals a number. So my vertical asymptote here is this is getting closer and closer to 0. That's my undefined value. So your asymptote happens at those undefined values. So my vertical asymptote here is going to be x equals 0. And then we also have another one for our horizontal. It's getting closer and closer to the x-axis, but it's never crossing it. The x-axis is the same thing as if y equals 0. So our two asymptotes here are x equals 0 and y equals 0. Again, those are going to be your invisible barriers. In fact, when we start shifting them, these values, this h and this k value, are also going to end up being your asymptote. So my vertical asymptote, when we start shifting these, is going to end up being at your h equals a number. And your horizontal asymptote is going to be at k. So it's going to be at y equals k. I suppose I could have written this as x equals h. So these are going to end up representing your asymptotes as well once we start shifting, and we'll get to that. So the other piece we're going to talk about with this is the domain and range. Think back to first semester. Remember, domain was all your x values, and remember, range is all your y values. And when we talk about the domain and range for these functions, both our domain and our range are always going to be all reals. If you guys haven't seen this symbol, this means all reals, except wherever you have an asymptote. So domain is x, so my asymptote is at x equals 0, so my domain is all reals, except x can't equal 0, because it's that invisible barrier, it's undefined there. Same thing for the range. It's going to be all reals except wherever your asymptote is. Here, my asymptote is at 0. So your domain and range for these functions are always going to be all reals except where there's an asymptote. Okay. So big thing to take away from here, those asymptotes are dotted lines. They're lines the graph approaches but never crosses. So let's try a couple. First, I want you to take a second to read through this real world example so you can pause it here and kind of read through that so you can see what this is used for. And then join me again when you're ready for the next problem. All right, so we're going to write the equation for each graph. We're starting with our parent graph. Remember, we had just discussed that if you're shifting this, this would be x minus h plus k. Remember, h is going to be your horizontal movement. K is going to be your vertical movement. So if I'm translating the graph 7 units left, left means horizontal, so it's going to be the denominator. Left means we are adding, so we have 1 over x plus 7. Then we want to find our asymptotes. Our vertical asymptote is going to be whatever that x value equals. If you think back to here, our vertical asymptote was an x equals a number, or x equals h. So here I'm going 7 to the left, so my vertical asymptote is going to be at x equals -7. Because your h value here is technically -7, because remember it's x minus a -7. That's how we get that plus there. Another way to think about it is you can get your vertical asymptote by always setting the denominator to 0. So if I'd set my denominator to 0, if I subtract 7, I'm going to get -7. So the vertical asymptote, you're always setting your denominator to 0, or if you can remember, it's just always that h value. Our horizontal asymptote is going to be kind of whatever we are adding or subtracting on the back. So here we're not adding anything, so it's going to be y equals 0. Again, I know it's kind of backwards of what you think, but remember our horizontal matches up to your vertical movement, so kind of backwards of what you think. So make sure you figure out a way that's easiest for you to remember which one goes with which. Okay, so horizontal asymptote is always going to be y equals a number. Vertical asymptote is always going to be x equals a number. All right, so let's try another one. Translate the graph 10 units down and 4 units right. So right is my horizontal, so that goes in the denominator. Right means I'm going to have 1 over x minus 4, and then down means -10. So that means behind the fraction, I've got the -10. Don't put that inside the fraction. That's a separate entity there. So then our vertical asymptote is with the denominator. So if we say x minus 4 equals 0, we're going to get x equals 4. And our horizontal is whatever's kind of adding or subtracting on the back, and it's y equals. So we're going to have y equals -10. And yes, it's very important that you put x equals and y equals. If you just put the number, you will not get full credit on a test or a formative check. I need to know that you understand one is x and one is y. If you kind of want a visual of this, we're basically taking the graph that we did and we're moving it. So if we look at the one we just did, if I were to kind of sketch this out real fast for you. So we're taking that entire graph and we're going to move it to the right 4. So I'd put a dotted line there. I'll do that in blue. So that would be my asymptote. And I'm moving it down 10. So this would be 1, 2, 3, 6, 10. Not to scale, obviously. So I'd have a vertical asymptote down here, or horizontal asymptote down here. So then if I were to graph this or kind of sketch in, it's a little bit bigger down here, our 2 branches, it's a little bigger down here, would have been moved. So we would have had a branch kind of come in over here, and a branch kind of coming over here. If you also want to pop that into a graphing calculator, I might be able to see that as well. So it's basically taking this graph that we made and it's moving it to the right 4 and then down 10. It's kind of a rough sketch of what it would look like. Okay, so again, vertical asymptote, denominator equal to 0. Horizontal asymptote is kind of whatever you're adding or subtracting on the back there. So let's try a couple more. Let's try doing it when they give you the horizontal asymptote. So here they're giving us, again, that function. Write an equation for the translations. So horizontal asymptote at y equals 3. So remember that matches up to the k. So this would be y equals, and a vertical at x equals 0. That means we're just having 0 in the denominator. So these would be our two asymptotes. Here we get y equals 3, and here we get x equals 0. So we're not adding or subtracting anything. Why don't you pause it and try B on your own first, and then when you're ready, check to see if you got it right. All right, so if we look at the second one, horizontal asymptote at y equals 11, and we've got a vertical at x equals -9. So this means we moved to the left, and this means we moved up. So we're going to have y equals 1 over x plus 9 plus 11. Okay, so just another way of thinking of it. So let's see if we can do the last three here. In fact, I would challenge you to try these first on your own and then see if you've got them right. So if you want to pause it and then come back. All right, so our vertical asymptote is always when it's going to be our x equals. Horizontal, remember, is always going to be when y equals. So our vertical asymptote, remember, is also when the denominator equals 0. So if I set the denominator to 0 here, I'm going to get x equals 9. And then our horizontal is always what we're adding or subtracting on the back. And if there's nothing there, that's just 0. And then remember, the domain and range are always all reals, except wherever your asymptotes are. So here I have an asymptote at x equals 9. So this would be x can't equal 9. And my range, I have y equals 0. So this means y can't equal 0. So let's see how you did on the second one. I always do the vertical first. So I've got x plus 5. So this means we're going to have x equals 5. Our horizontal is whatever's on the back. So this means we're going to have y equals -3. My domain is going to be all reals except where that asymptote is. So that's going to be x can't equal 5. Our range is also all reals, except it can't equal where the horizontal asymptote is. So that's going to be y can't equal -3. If we move to the last one, again, hopefully you tried this first on your own. Our vertical, we've got x plus 1 equals 0, which means x equals -1. Our horizontal is whatever you're adding on the back, and that's y equals. So we'd have y equals 18. My domain is all reals, except x can't equal -1. And my range would be all reals, except y can't equal 18. So hopefully you're getting better at these. I know it's the first day of it. The key is, remember, the denominator goes with your vertical, and the horizontal goes with whatever you're adding or subtracting on the back. And remember, your horizontal is y equals something, and your vertical is x equals something. All right, last thing, see if you can match these. Try them first on your own, and then when you're ready, come on back. All right, so if we look at the first one here, it looks like we had a shift. We went to the right 5, so we kind of have to figure out where would we have a vertical asymptote of 5, and that looks like it's here. If you look at, it's got an invisible barrier here. So this one is going to go with A. If we move over to the second one, this is going to be when my asymptotes are going to be when x equals 0, and I'm not adding anything on the back, and y equals 0. So the graph that has asymptotes on the axes is going to be the first one here, which means process of elimination. This is going to have to go to the middle one, but we can check it. So here, this means we're going to the right 3, so we have an asymptote at x equals 3, and we went down 1. So if we look here, you can kind of sketch this in. It looks like we have an asymptote at -1 and at x equals 3. Okay, so you kind of have to be able to go both ways, whether you're matching or whether you're saying them. Okay, so make sure you do the assignment. I put a link there. It is a worksheet, so you can write your work on a separate piece of paper and then upload it to Schoology to that homework document. And then make sure you do the second lesson this week, which is more graphing. And then Friday there will be a formative check. So I hope you're off to a good week.